let's continue with the next presentation. Let me introduce Jan Hudec. Jan Hudec is going to present metal 3D printing technologies at Missan company. Jan,
okay, so thank you for the introduction. I will turn on my presentation that will show the overview of the metal additive technologies that we deal with in Missan. I'm actually a production application engineer at Missan. We are not really involved in any research project. We don't even produce parts. We simply deliver the production technologies to companies. And I was invited to just briefly introduce the different metal additive technologies here, to give some basic information preceding the following presentations of the following speakers. So let's take a look at the metal additive technologies. We will now speak mostly about two of those, and then I will just briefly introduce another two. The first one is the most frequent, most used, is the laser powder bed fusion. Then I will continue with electron beam melting, which are mostly related also to medical applications. Then I will mention direct energy deposition and binder jetting, but these are not really suited for medical applications, at least not yet. So laser powder bed fusion, you may also know as the SLM or DLMS. It's the most well-known technology when you just apply a thin layer of metal powder that you then melt with laser, and then you will apply another layer, and then you can melt another layer on top of the previous one. So this is basically the principle of this technology. We can build parts from stainless steel, aluminum, Inconel, cobalt, chromium, also some precious metals, but one of the most frequent applications is titanium. It can be either Ti-Li64, or it can be a commercially pure titanium as well as some dental certified titanium. So what are the most frequent applications here? Well, actually in Czech Republic, the most frequent application is the mold industry, when you can build some cooling channels to increase the productivity of the mold and increase the quality of the parts that you inject in the mold. Then worldwide, aerospace is also a leading application. You can build some topology optimized parts. You can merge assemblies into one part to cut costs in aerospace, which is the most important thing to save on cost and also to save on fuel consumption. Then not so often it's used in automotive, but it's usually just for prototyping and motorsports. Jewelry is theoretically also possible, but in Czech Republic and Slovakia also we have some medical and dental customers. The reason to use additive manufacturing with metal additive manufacturing in medical is to produce either customer-specific parts like cranial implants or facial parts, like or jaws. But you can also build trabecular structures to support the tissue ingrowth to mimic the bone structure. So you can see here some hip implants, spinal implants as well. The dental market is also very popular. and they use additive manufacturing quite often, especially those large dental laboratories that have enough workflow to saturate such a machine. And in that case, it's the most economical way to produce crowns or other dentures. The machines here are quite well, there is not such a wide variety of machines. There are small machines that can be suitable for those dental implants that have really a small build plate, 90 by 90 or 100 by 100. Then for the medical, like implant, hip stems, and this kind of implants, there is the regular 250 by 250 machine that we also have at least 2 customers here that produce parts from titanium for medical purposes. There are also some larger machines, but they are not used for medical applications at all. Electron beam melting is the younger technology. It's more specific, but it has advantages. The main difference here is that it doesn't use a laser, but it uses electron beam emitter. So it uses electron beam energy to melt the metal powder layer, and it takes place in vacuum. So the whole process is it's a hot process. Actually, you can keep really high temperatures in the chamber. It can exceed also 1,000 degrees, and you have the possibility to stack parts one on top of the other. So that's a really big deal in aerospace and a medical sector. When you go for productivity, this is usually the way to go. Small difference is that it does not need as many supports as a laser powder bed technology, but the parts are created in such a powder cake. You can see here on the picture in the left bottom that here there is a cake half blasted away. These parts are trapped in such a semi-sintered, semi-glued powder that you have to blast away. The good news is that the blasted powder is again recyclable, and you can use it again in the machine, so you don't lose that. You don't lose this powder, and you can reuse it again. And then you do some post-processing, like machining, whatever it is necessary. As I said, it's used for medical and aerospace technologies. Another big advantage here, apart from the productivity, is that you can produce parts that have very good fatigue properties. They can also work with higher temperatures. That's why the turbine is here. So these are the parts that you can spin up, and they will do just fine. The properties are usually higher than you would get with forging. So if you apply hot isostatic pressing afterwards, then you're able really to increase the toughness of this part to the maximum. And if with electron beam melting, it's not really suitable for customer-specific implants. It's mostly used for those series produced parts like hip cups, hip stems, and these things. And if you go for this high productivity, the cost per part is usually just 50% compared to laser technologies. So if we should compare electron beam melting with laser beam, technologies. The process is in vacuum. It has better heat absorption. It's usually 70% compared to just 30% of laser. It has much higher productivity due to the higher electron beam power and speed and the movement speed. It can be suited also for more robust parts and less support structures. And as I mentioned, you can stack the parts one on top of the other. Here you can also see the powder cake is blasted away, but it's still it's still sticked together. But you can crack it away. We have less materials, but that's usually just because of the typical applications. So with EBM, we don't really have any aluminum or steel because it doesn't really make sense to produce parts from these materials. The rougher surface may be disadvantage, but it can also be advantage. And I mean, in the medical applications, this is usually considered as advantage because you don't have to only rely on the geometrical macroporosity, but also the surface roughness helps the implant to be accepted well. And we've got some geometry constraints. That's due to the powder cake. You cannot really do any channels inside of the parts. So where you cannot reach with the blasting gun, the cake remains there. With lasers, the process is in an inert gas, so it's such a cold process. The surface is usually more, it has better roughness. You can produce inner geometries if that's your aim. You got more materials and applications, machines with different build sizes. And we can also do hybrid builds. That means that we can continue with 3D printing on top of the existing part. That is not possible with EBM. But afterwards, there is usually a stress relief heat treatment necessary. That is not a case with electron beam. And the parts are welded to the build plate, so we usually build only one layer of parts, and then we have to remove it, and that can be time-consuming. And the final powder also involves higher safety measures. So these are cons and pros of these two technologies. So the first one is for, well, it's more focused on the aerospace in this presentation, but yeah, it's for more bulky parts, for parts where you need a lot of melting, and where you need a lot of parts to be produced in one go, so you can stack them on one on top of the other. With laser technologies, it's usually for very lightweight parts, structural parts, thin-walled applications. I prepared also another two technologies, but these are not really suitable for medical applications. So that's just for you to have a wider idea about metal 3D printing. So you can have also metal printing head inside of a 5-axis machining center. That's, for example, from Okuma. Imagine a machining center with a laser head and a powder delivery. This way you can put some more material on top of existing machined part. It can also be a cylindrical part or some general round-shaped part. You can also do some laser hardening or hard surface coating if if it was a point of your interest. I had a video here, but I will skip that. It's not so important. The last is the binder jetting technology. It's the youngest of technologies, actually. It's in preparation. So what is this technology about? Still, we have a metal powder. We still layer the powder in thin layers. But we don't use heat to melt the powder. Here we just put binder with the print head on it, just to glue the powder together. And then we take out these parts and put them into debinding and sintering oven. As you can see on the picture on the right, there is a very certain disadvantage of this technology, and that's the shrinkage during sintering, which can be up to 30%. But the advantage here is that the speed of build is 100 times faster than with the most frequent laser powder bed fusion. So this cuts costs lower quite significantly, and you have much more higher productivity. As I said, this technology is not yet available for commercial purposes. These are the first machines are now at the key customers for evaluation, and I'm not sure if we have any titanium applications yet, but I think stainless steel is viable. So maybe it can be used for some tools for medical industry as well. So that was all from me. Thank you for your time. If you have any questions, you can ask me or you can contact me later. Our region is mostly Czech Republic and Slovakia, but also if you are from Austria, I think I can give your contact from someone who can take care of you in Austria as well. So thank you for your attention.
Thank you for very interesting presentation from the industrial side. Are there any questions from the audience? I want to encourage the audience, the participants to ask questions. So far, I have to ask always after the presentation, but no problem. The presentations are very interesting, so I can do it also in this time. So if I understood well, Nissan is actually developing machinery in all three different fabrication processes: electron, laser, and also binder jet. Is it right?
Actually, we represent companies that produce these machines, so we are basically a reseller, but we also do a maintenance of these machines on our market. So we actually are the applicator of those technologies. So if a company contacts us, we can discuss if it is suitable or which technology they should use, if there is any way that we can optimize their production. Our other range, well, the bigger range of our business is actually machining technologies with robots and automation as well. So we do turnkey solutions for factories. And in the medical segment, we have several customers in Kladno and in Brno that produce medical implants from titanium. One of them is more focused on veterinary applications, actually, and the other does cranial implants and special patient-specific parts. And then there is another customer in Slovakia. They are dental oriented, and they already have expanded their facilities. They have 2 machines already, and probably are getting a 3rd by the end of this year. So this segment is growing as well. So this is our focus.
Maybe very shortly, the second question. I realized in your presentation that in some of those three processes, it is possible to print on existing object. Would you maybe explain how is this done? Because in the powder bed, I cannot imagine how this is done.
Yeah, this is possible usually only with the laser powder bed fusion, which was the first technology. You can basically start printing on a build plate, but you can also start building on an object other than build plate, as long as the top layer is perfectly horizontal.
Mm-hmm.
So you just clamp the part to the build plate somehow or glue it to it, put powder around, and then you will just not start at the beginning of the build plate, but in a different layer, in a different height, and you will only print the remaining geometry on top of the previous machined part. So that's the idea.
Thank you. Interesting. Yeah.
Okay.
Thank you again for your presentation. It seems there are no other questions from the audience. So let me introduce the next speaker, which is Libor Beránek from Czech Technical University. He's also going to speak about manufacturing of metals. So Libor, the floor is yours.
So, good afternoon, everyone. I hope you can hear me.
Yes, we can hear you well.
And now I also hope that you can see the presentation.
You can see the presentation in the presentation mode. Perfect. Thank you.
So, hello, everyone. I just want to introduce basically our faculty of mechanical engineering, Czech Technical University of Prague, and what are our capabilities in additive manufacturing of metals and also in different ways of inspection of parts we have. So the goal and what we are trying to offer to our industrial partners is the whole production, or we can call it product chain, from design of the part for additive to its final non-destructive testing, even some destructive testing. So the complete chain, starting with structural optimizations of the part, because maybe, or I know that you already understand that the most efficient way how to use additive technologies is to have right design of the parts for additive technologies. So we have the experience and also the tools, so we can provide structural optimization of parts, whether it's topology or lattice optimization for specific application. From this design, we can basically verify our build preparation using simulation softwares. That's mostly about orientation of the part, support configuration, and prediction of the outcome of the deformation or potential failure. And we can do these steps before we start the process of the printing. So we can not only design the part, but we can also prepare the process and verify it before the actual production. So we skip some major mistakes. We have two production technologies. Basically, one printer is smaller. It's a concept laser, or now G additive machine. And the second is TruePrint 1000. One has a building volume of 250 by 250 by 270 millimeters. This is the concept machine. And we can switch materials, and we do so in some campaigns. So we are able to print aluminum alloys, tool steel, Inconel, and so on. We can also print titanium. We are equipped to it, but this is not, I would say, so common material for us. Then for the TruePrint, this is a smaller printer with a volume of 100 millimeters in diameter. And basically the volume, or the building volume, is a cylinder of diameter of 100 millimeters and the same height. And this one is dedicated for IC 316, so for stainless steel, basically material. So smaller parts, small samples we can print there, bigger parts on another. Then basically right next to the room with the printer, we have all additional technologies that you need. We have our own heat treatment up to 1300 degrees with inert atmosphere using argon, with fully computer control programs, so we can do our own heat treatment, whether it's residual stresses release or whether it's some quenching and hardening of the material. Then, because basically our department focus is also on machining, process planning, and metrology, that's the name of my department. So we have a lot of additional production technologies where we can finish the parts from additive. So we have several CNC machines, and also we have some experience how to design the part. The first step, how to prepare the build, so we can later finish it, maybe even on the pallet, on some CNC machine. So this is, I would say, also important step. A lot of parties are not having the full production chain, and then they are struggling with finishing their parts with some automated technology. For the quality inspection, basically we have several CMM machines, whether tactile or optical, and we have also some non-destructive testing, meaning we have computed tomography. So we can inspect the part not only for the dimensions, but also for some internal structures and the porosity inside the material. And we can give you the feedback, or we usually provide the feedback for ourselves to optimize the process to, for example, limit the porosity and so on. Then we have also laboratories for metallography analysis, but that's usually destructive testing. So we can also see inside the material in such a detail. And based on this production chain, we are also trying to basically transfer this know-how to industrial partners. So not only on some specific area of design, production, but we are trying to put it in some, I would say, context. Usually because the design rules for the 3D printing, the orientation of the build, which you can predict using some simulation software, you can predict some potential errors that may occur, but you cannot predict what will happen during the machining or how the part is supposed to be aligned on the CNC center. So it's, I would say, it's good to have it under one roof to understand the context when you choose certain orientation, what will be the limitation for the machining, for example. So this is something what we are trying to transfer to the industry. Maybe this is one of the more complex projects we have made in the last years, and this is basically a topology optimization of the brake shield bracket for a military aircraft. The brake shield bracket is, this is the orange part. Basically, this is a part of primary structure of the aircraft. So this is a critical component, and it has to be certified as such. So basically, we were responsible for the design of the topology optimization, and then for the machining of the part itself. The printing was done by another partner in the consortia. So here you can see some preliminary studies. Here you can see a final design. Here is just a comparison for the visualization of the original design, the new one. Here is the final process step. Maybe I skipped the results of the inspection here, and this is the final piece. And the piece was also tested, so it can be really mounted into the aircraft. So we have gone through all this process with one of the aircraft producers here in Czech Republic. Another application which is suitable for 3D printing, the first one, we can call this lightweighting. We are trying to minimize the weight of the parts, and whether it's for aerospace industry or whether it's for some car racing or motor racing projects. Everywhere you want to reduce the weight, the topology optimization or the structural optimizations is a process which can help you to reduce the weight, and then additive manufacturing is a good way how to make these complex shapes or how to make these complex parts. The other application is conformal cooling. That means trying to do better cooling channels in the molds, whether it's for aluminum casting, for example, high pressure die casting, or whether it's for injection molding when you are working with polymers. So the conformal cooling basically helps you to solve some problems. This was the original, for example, porosity or lunker within the gearbox housing. And you can see that you can prevent these non-conformities when you can cool this specific place faster than the rest of the material, then this will not occur at all. So you can see that this was basically one of the first steps with cooperation with Škoda Auto on this insert for basically 1/4 of the mold. And the other step, which our students who are involved into designing this and also into application of this, was basically the whole quarter of the mold was 3D printed with complex cooling channels, and it was installed in the serial production. And also we have some real technical and economical data from this application. So we have also some experience with application of this tool into the serial process and with certain maybe step backs which you have to face when you introduce this technology into the tooling, basically. Then the presentation, we don't only have the production technologies, we have also inspection technologies. And this is just a simple, I would say, visualization what the computer tomograph may offer you. So the first step, it's a measuring instrument. We have a metrology computer tomography, which is called Metrotom. So that means it's also serving as a measuring machine. It has measuring errors. So it's really a measuring equipment. So you can provide some calibrated measurements, distance measurement, coordinate measurements in general. Or you can simply just compare the nominal data, which are given by the CAD model, and the actual data, which is a point cloud, which you get from scanning from the CT. So this is a very quick analysis on such a part, which is basically, this is a bicycle part, the midsection of the bicycle printed from aluminum alloy. Scanning in this case is something like 40 minutes, maybe 50 minutes. And this kind of analysis is another 5 minutes. So this is a very quick analysis to get, and you have complete information of the outer shape and also of the internal cavities. Then, of course, using computer tomography, you can also see inside the part. So here you can see some cross section of the part, which actually in the software is live. You can go through the data with also some viewer software that is freely available. So once you have the scanning data, you can work with them independently, basically, of us. This is one of the analyses which can be provided by computer tomography. This is a midsection of basically high fatigue samples or samples for high fatigue cycle testing. And you can see that there is quite significant porosity. This is the original 2D image from the CT scan. You can see the visualization of the pores here in 3D, and you can get also some kind of statistics. So you can see that this sample was actually very bad, and it had almost 4 or more than 4% porosity. So you can see on the histogram, you can see the distribution of the pores. You can see a location and the size of every single pore within the resolution, I would say. And the resolution is something like 1/100th, 200th of millimeter on the steel, which is attainable. Maybe I should mention that this is not our product. I don't want to mention the party which was printing these samples, but this is some real data analysis made 1 week ago, maybe. Then, of course, we can analyze surface texture. As most, I would say, laboratories, we have some confocal microscopies, so we can describe the surface of the part using whether roughness, waviness, or some spatial and volume parameters, as is, I would say, pretty common today. Regarding inspection, we don't have to finish with the inspection, but as I mentioned, we have some experience with some also special finishing technologies. So we have developed for another aerospace company a technology for polishing components, and few of those were also 3D printed. So this is some stage of development of the polishing technology, where we basically, because these parts are quite expensive, when you want to test more process parameters, you have to be able basically to cover part of the workpiece to use it maybe 10 times for different production parameters. So we have designed several, again, additively manufactured masking fixtures. Then we can get from one part, we can do, for example, 20 process parameters. We can test them and we can optimize the process. And this part was, again, 3D printed, and this may be final stage of the surface which can be achieved. And of course, this is usually, again, optimization between the surface roughness and the geometry precision of the part, because usually all the polishing technologies are affecting the geometry of the part in the negative way. So you have to find some kind of compromise. So this is basically what we are doing here in the area of additive manufacturing, and we are basically offering our capacities, or we are quite eager to cooperate with anyone who is doing research in this area. Also, the CT is not only for, I would say, metal additive manufacturing, but it's also quite a powerful tool for all the polymers production technology, whether it's 3D printing, whether it's injection molding. It gives really very quickly detailed results of the parts. So this is everything from my side. If you have any questions, I will be really glad to hear them.
Thank you for your presentation. There is one question from the audience. How often or why do you combine 3D printing with CNC post-processing?
I would say every time where the part matters, when it has to be installed somewhere where you need precise specifications. On the printer, when you see the part of maybe the bracket, this is the typical part. Quite a big part. This is like 200 millimeters across. I hope the image is still available to you. The deformation of the part after printing is sometimes even close to millimeter. So then you have to be able to manufacture all these surfaces which has to be assembled with the counterpart, and you want to have the specifications far more precise than 1 millimeter. For example, in 0.1 millimeter or 0.05 millimeter, then you usually have to machine it. Also, the surfaces from the bottom, which are sitting on the wing, has to be quite precise. So then you have to machine it. So it's very difficult to have a big part even from polymer additive manufacturing, whether it's metal, polymer, doesn't matter so much. It's very difficult to keep the precision under, for example, 0.1 of millimeter. So I would say I've never seen an application, or I've seen an application on one company at Honeywell, but the turbocharger wheel was something like 30 millimeters in diameter. And then they were able to keep the tolerances under 1/10 of millimeter. But usually the deformations are much bigger. And if you want to assemble it together with other parts, then usually the surfaces that serves for the assembly has to be machined.
It seems that the answer was satisfied. Thank you. There is another question from Branko Radicevic. Branko?
Yeah. Sorry, maybe I missed it in the beginning of presentation, but is it possible to print multi-material parts so that contain more than one material simultaneously, let's say steel and aluminum?
Not on this specific technology, not on this powder bed technology, but in the university we have, I would say, few other technologies that can do so. One is wire arc additive manufacturing. You can combine different wires, basically. It's maybe not so precise technology is this laser melting. It's more productive, and you can combine materials. And then we have plasma transfer arc, PTA technology. So you can also use plasma to weld different powders together, and you can combine the powders. I don't want to say freely, but you can combine different materials using the technology also. So this powder bed technology is not the right technology to combine materials, but we also have others.
Okay, thank you.
Okay, thank you again for your presentation. Yeah, the next speaker is Guillaume Clement from Haratech. Guillaume is going to present about 3D printing and medicine, current possibilities, hardness, and perspectives. Guillaume.
Yes, thank you, Pavel. Hello, everyone. I might correct straight away. Maybe I will not be talking only about 3D printing and medicine because this topic has been already covered before. So I just adapted a little bit to the consortium that has been presenting today. Hello, everyone. Again, I will start to present and see where is the best. Give me a minute. There. So here, my second screen. And you should see my screen presentation mode now, right?
Yes, it's okay.
Okay, perfect. So, yeah, as I said, I allowed myself to modify a little bit this presentation topic from 3D printing in medicine because it has been already extensively presented into 3D printing at Haratech more in general, because it's a topic where we're involved in many different ways, as you will see. Yes. I will start by giving a rough overview of what Haratech does, because it is quite various, and you will see why I cannot only speak about the medicine field, then go more into detail on the 3D printing capabilities that we have here, and one example that we had in a research project in the medicine field, which is called jaw implant. Yeah, I will give more detail later. So the motto of our company is from the first idea to the final product. We're a team of 18 persons in the conception and in the fabrication of plastic parts. So we have really the whole process in making plastic parts, in designing them, conceiving them, simulating them, and then in the end producing them. In different topics, so design engineering, yes, simulation, which is a help for the conception, excuse me. Project management, reverse engineering, and then all the manufacturing technologies such as 3D printing with the help of 3D scanning, vacuum casting, CNC milling, injection molding is not here, but you see it's a whole, the whole branch is actually covered by our company. Some hard facts, maybe it has been created 18 years ago, I got it, by Manfred Heiberger, the nice young man that you see on the picture here. We are seated in the Tabakfabrik Linz. So it's an old tobacco manufacturer that is slowly being renewed to host more and more companies. You can see a rendering of how it should look like in 2-3 years' time. We are, as I said, 18 employees, and we have had more than 1,000 different customers, from the smallest company and even private persons up to companies like FACC, the plane equipment manufacturer, or Rosenbauer, which makes parts for firefighters, and so on. But not also in development projects, but also in research projects, as we have at least submitted 50 project proposals. Unfortunately, not all of them have been accepted, but some of them we have been working on them for years and still current, not today. Yes, as I said, we supply the full range of plastic solutions, from the first idea really to the final product with all the steps in between, and we are proud to have the ISO 9001 certification for quality of our processes and fabrication. So to review the different steps that we covered, the design department, we have industrial designers, talking with different actors and defining the needs, and then coming with the best mock-ups. We also have our own capabilities in conception and simulation, so CAD design of parts and molds, and helping with injection molding simulation and also mechanical simulation, so where we can simulate the flowing of the molten plastic into a cavity, its cooling, its warping, the thermal effects and aspects in the mold itself, in the part itself, the impact of different types of cooling, different materials, different geometries, different materials in the part and in the mold itself, glass fibers, carbon fibers, different kinds of fillers, everything basically. Another interesting topic of the design part is the 3D scanning and reverse engineering. As you can see on the left side, we have the mobile scanner with the help of which we can then scan objects of basically any size. Or we have also a body scanner on the top right corner that scans a person in 30 seconds. That is helpful more for private customers and also in the fashion industry. If we're talking about more precision scanning, then we use the left-hand scanner. That helps us to do production control, as you can see with this rendering here with the different images, where you can measure the difference in geometry, the dimensional tolerances between what should be the right part and what is the right part, but also recreate an object from the 3D scan. So any object that exists, even if we don't have 3D files, then we can reconstruct it afterwards, modify it, make a mold, make a 3D print. Yeah, that's a big help in the tool manufacturing, in the part manufacturing. And if we then move slowly into the final product, we have the steps of rapid prototyping and prototyping in itself with a lot of different activities. 3D printing, of course, in the top left corner, in that case, filament 3D printing, but also assembling of models of parts together, painting them. For the obvious ones, in the top right corner, there's a laser cutter, which is very handy. And in the middle, at the top of the bottom of the page, you see also an injection mold, which is made of aluminum, and we also have the capability to make the cavity out of 3D printed out of plastic, which is so really a hybrid version between the serial production and the prototype production. Because prototype production is very agile, is very enables to have a lot of changes in the design, to have a lot of iterations, and to find really the right product, but with the drawback of not providing the right material, or not the right tribology, not the right inner molecular structure of the plastic molecules, for example. The extreme case is the FDM or FFF technologies, where plastic is applied slice by slice, so it's highly heterogeneous and is not showcasing you the final mechanical properties of the product if you intend to make it with injection molding, for example. One solution for that is to use aluminum instead of steel to make an injection mold cavity, which is easier and cheaper to mill. So it goes faster, but you still have to count a few thousand euros just for the cavity, and then for the tests, some more costs. So 3D printing the cavity is even one more step towards hybridization between prototyping and serial manufacturing. And I've put on the top right corner a picture of a vacuum casting machine, excuse me, that we have. We have more of them internally, which is then the step, let's say, even before the injection mold, where you can cast a lot of different parts with a high accuracy and detail, level of detail. But again, the material is not exactly the same as injection molding. As in injection molding, it's a bit better than 3D printing, but not the best. Depending on the size of the series that is to be produced, depending on what material we need, speaking about the mechanical properties, the optical properties, the chemical properties, and the precision that is demanded, and the amount of man work that is allowed to be on this project, then one or the other process is being chosen. That is why I also put the vacuum casting image on the serial production, where on the right side you see vacuum casting again, because sometimes it's serial production is about 50 parts. In that case, it makes no sense to make an expensive injection mold. injection molding machine that you see on the left side, we have two machines with different capabilities so that we can inject a wide variety of materials. And as you see in the middle images, we have also the capabilities to make our own molds, as I said, prototype or serial production molds. Just to finish the overview of Faratech company, some project examples. It could be either for OEMs. So here you see that we have been producing parts and still are producing for Fronius, for Keba, Gainspeed. On the right side, you see also for Rosenbauer, a product that is has been lastly being shown. Yeah, very interesting in various projects that are running since years for some customers, and always very interesting. Not only OEMs and big companies, also small and medium companies we're working with for some models. Some on the right side, you see a safety module to protect against break-in for window handles, for example, or some air quality measuring device, emergency signs. So the application fields can be very various, and we're used to talk to such different customers, actors, suppliers, and this is really demanding and as well as interesting, because every time we have to adapt to new needs and to new level of precision, accuracy, timing, costs, etc., etc. And of course, I cannot go without mentioning startups, which we have been working with a lot in these past years. Again, a lot of different things. Superflat is a chair for babies. Starkey is a health device that is supposed to help the hand joints thanks to vibrations. Vital monitor is also for health devices. Some hair dyeing equipment. The handles here are called Gemba, Gain mit Bands, some sports device, or also, for example, the Freeze on the right side, just a glass cooler, but again, new customer, new perspectives, new fields, very interesting. And of course, some research project here, as various as the previous one. So to go quickly over that, some bone implants in the some bone implants that I mentioned in the first place. Research project in the music industry on the left side with harmonica accordions, and on the right side 3D printing into fashion with biosourced and biodegradable products to produce shoes, for example. If I might go over now 3D printing more in detail, all these technologies are available at Faratech. So I will go quickly over them because I suppose that most of you know already about most of these different variations of plastics additive manufacturing. But yeah, the most famous one is FDM, or the more generic name FFF, fused filament fabrication, where we have a wide variety of material, easy of use, most of the time with open systems, so you can tinker around with the machines. And this is a long-lasting technology already. Yes, with the drawbacks that we know, it's not that precise, has a very rough surface compared to the other technologies. And as I said before, it's very heterotropic, but still very easy to use and very popularized. PolyJet from Stratasys is, of course, to be mentioned because of its high accuracy and the wide variety of textures, transparencies, hardness, and colors. Oops, I forgot an R. Colors that it offers, and all the shadings that are possible. I know that Stratasys presented a new machine 1 year ago, I think, that enables to print all the different colors from the Pantone color scheme, color panel. So up to, I think, 30,000 different colors, something like that, like in that amount, roughly. But if the parts are very beautiful, they are maybe not as long lasting as some other process. Stereolithography is not to be presented anymore, the first of the 3D printing processes. Color jet printing, in that case, it's the same as multi-jet fusion, as we'll see later. It's a powder bed but with gypsum powder and with a binding agent and with some color agent. Yes. So it's very dimensionally stable. The material is holding for a long time because gypsum, but of course it is fragile, it is heavy, and we have only this material, so it's limiting on one side, but at least you have the advantages of gypsum, which is actually quite rare in 3D printing, except ceramics, but ceramics are very expensive and small scale and very for high-end applications. SLS, selective laser sintering, not to be presented again. Very easy, only one material. That can be an advantage and a drawback at the same time. And here is some applications, for example, in our case, for some structural part, but most of the time for jewelry, because it doesn't need any support material, so that we can achieve very high level of accuracy. And multi-diffusion, same as the gypsum powder, but this is plastic powder from HP, which is very handy for most of the time for functional prototypes, because of its acceptable accuracy, I'd say, for most everyday applications, and because of the very nice mechanical properties. It can bend, it can withstand high stresses. It is, yeah, very interesting. Right, after this horizon tour, I would say a few words to one typical example and very interesting example of a research project in the medicine world that we have had the chance to work on, the jaw implant project. We have been working on two aspects at Heritage. One's the CAD design, 3D design of the implants themselves, and on the other hand, on the printing of the material and the testing. On the CAD design itself, this is here the rough strategy. Apply on the cube first for better comprehension, generating a few points in a volume, more or less, depending if you want it more or less porous. Then generate those cells around those points, thicken the beams between the edges and the points of the cells, and in the end round up everything, of course, where we can play around with the different thicknesses. So this has been done thanks to Grasshopper, so another Rhino 7, and which is another CAD program that is very handy, and Grasshopper, which enables coding and 3D modeling at the same time, which is very handy. So again, another aspect of our job, another variety of the occupations that we can have in the frame of our work in development and research projects. So, and if these techniques gives us, for example, this nice porous, here I think it's a part of a kneecap, of a knee joint here, and I have applied my algorithm to make this nice porous structure, but we will see the use case just after. For example, someone has a bone defect in the case, and the focus of our project, it was focused on the jaw. So first of all, we extract the data from a CT scan, so 2D pictures in the X, Y, and Z axis. And on the left side, you can see this green shades of green, where we just chose different shades, different intensities of on the CT scan images. And one density gives one color. So just by changing the color range, we choose the density that corresponds to skin, muscle, internal organs, bones, etc., etc. Thanks to this program, we can then extract, which is called InvestCellus. It's for free. We can extract then the 3D shape of the bones, as you can see on the left side. And in the case of the jaw, it's quite useful that most of the time it's damaged only on one side, so we just have to take the other side, the healthy one, mirror it, and then generate the shape of the implant depending on what we want to achieve. And for example, here you see this implant with the right side, you can see the part that will be inside the joint, in the ball joint, and on the left side, all the holes for the screw for maintaining it on the healthy bone. And after that, I will extract what needs to be the internal frame that it's made of titanium, 3D printed, to give some structural strength so that the patient can chew just a few days or weeks after implantation. And afterwards, it would be a shell made of 3D printed. There would be the MET 610 material, or also there's a PCL, polycaprolactone, that we have tested that are also very promising. And those material are bioresorbable in 3 to 9 months, if I remember correctly, in the body. It means that then the bone will grow from itself afterwards and generate some new bone cells, which is the golden goal of grafting technologies then not to have any foreign, how do you say that? How to have any external elements inside the body at the end of the intervention. So in that case, we would still have the titanium part that will still remain there until the end of the patient's life, but at least most of the plastic would be renewed by the own cells on the patient, which would be the best in terms of biocompatibility and to long lasting of the implant itself, because it's being renewed on its own. And yeah, we have made then some 3D printing tryouts, and we have printed these small cylinders. They have been implanted into, the bone of a lamb, and the lamb has lived for 3 or 4 months with this, has been then sacrificed, sliced, and observed in the microscope, and to say things quickly. And this project has given very positive results regarding cytotoxicity and regarding bone marrow cell growth afterwards. So yeah, the project unfortunately stopped here because we're at the end of our 3 years, and we are currently trying to make this project, to continue this project, to pursue it, to go towards a final suiting and human-oriented solution. That would be from my side. Sorry for taking a little bit too much time. If you have any questions to anything that I just presented, you are very welcome. And else I will give it
Thank you, Guillaume, for your presentation. There is, I don't see actually any hand raised. Maybe in the meantime, because I know that you as a Haratech also actually Profactor, we are within the same project within Reframe, printing on textiles. What's your experience in this field? How do you see it in the future? I mean, decoration or functional devices 3D printed on the textile. Guillaume, can you hear me? Okay, so let's. It seems that there are some connection troubles. No problem. So let me introduce the last speaker, which is Martin Krištof from Robert Bosch České Budějovice. He's presenting 3D printing in Robert Bosch České Budějovice.
Good, thank you. Good afternoon.
Good afternoon.
1 moment, please. Share my desktop. Yes. Okay. See then my desktop, please.
Yes, I can see your presentation, but not in the presentation.
Okay. Okay. Let's take. Oh, no.
Yes, now.
Okay.
Yes,
thank you. So, thank you. My name is Martin Krištof. I work for the company Robert Bosch in České Budějovice in the department of the Technology Center. Short overview: our plant is manufacturer of the plastic components for the automotive industry. In the past, has been dynamically developed, as the last investment was building a development technology center, and it's here. And our 3D printed team is placed directly in this small building. So short overview, our products and development activities. We are a producer of the plastic part for the fuel system, as for example, these fuel modules and pumps. Here you can see some the Denoxtronic systems, fuel rails, accelerator pedals, and here is the air management or the different sensors for this air management or exhaust systems. we develop some the competencies for the future, as for example the applications for digital transformation, data analysis, and 3D print. Today I would like to introduce our activities in 3D printing area. Our primary focus is on the printing of prototype parts, jigs, and prototype injection tools. At our disposal, we have 3 different technology. The 2 for the plastic printing is the technology PolyJet and FDM, and the 1 for the metal printing. Technology PolyJet is very powerful 3D printing technology that produce smooth, accurate parts, prototypes, and tooling with microscopic layers. Here is the minimum building layers is 16 microns when we use the single material. We have a very small accuracy around between 20 and 85 microns. We can produce thin walls and complex geometries. This machine is from firma Stratasys. The type Object 500 Connex 3. Object 500 mean this build size is 490 times 390 times 20 millimeters in Z direction. And Connex 3 mean we can combine 3 different materials, and 1 material as the support. The materials are on basis acrylic resins, and we can in one printer task we can combine construction materials, for example, with the rubber-like materials, or the colorful material with the transparent material. This third material is the support, and this material is as wax, and this material is can be with water jet removed from the part without the big impact to the surface on the part. We print some prototype parts as for the assembly tests, and precision, you can say the master models for the setting the fixtures in the production lines. As for example, here this is the gas pedal, or here is the fuel rail. It was printing for our development center. We need see how flow. This body is from the transparent material. Some ejectors are from the serial production, but we need see, for example, the rest of fuel in the system, or it was not fuel, it was the water, but because it was oriented to the water injection. Generally, the materials for the PolyJet technologies are not fuel resistant. And because we produce the part for the fuel systems, we time to time got some we got some offers for develop or produce some parts for this fuel system, and we need to use some injection molding tools. We are able with this technology print some cavities and inject the original material to these cavities. The big benefit is the lead time, because in our plant we have some tool shop, but this tool shop is oriented to the serial production. We need both these prototype tools in external supplier, and here the lead time for aluminum or soft steel prototype tools is up to 10 weeks. With this PolyJet technology, we can reduce this lead time to 2 weeks, because on the first 1 or 2 day we are able to make some tool construction, included, for example, the mold flow simulation. Overnight we print some cavities, some inserts. In the next day, we set up these cavities in the universal frames, universal steel frame. Yeah, we have prepared some universal ejection system. And on the beginning, the next week, we go with this tool on the injection machine. Our department has 2 injection machine, and we don't need wait for the free capacity in the production line, and we can make some sampling, or we can make some sample directly by us, and after this we can make some the check quality, and on the end the next week we can send this part to the customer. Here is some example. The part is cover for GPA, this special step engine, and material, injected material was the polyamide 66 with 35% glass fibers. This ultramide. The injection temperature is over 320 degree, and it's of course the lifetime of this tool is shorter as a steel tool, but for the first trials, for first part is enough. The next technology is FDM. We use in our department or in our plant many small, this very famous Czech printers from firma Prusa, and in very different modifications as the single printer or as the multi-material, or I mean multicolor printer. The maximum build size is 250 times 210 times 210 millimeters, and accuracy is between 50 and 200 microns. The minimum build layer is 0.05 millimeter, but usually we print with 0.15 millimeters. This material is standard thermoplastic material in filament, and we can print with ABS materials, PLA, PET, HIPS, nylon, and so on. And we are in contact, or we cooperated with the suppliers or developers of filaments, and we test some of the new materials in the market, as for example a polyamide with carbon fibers, a polyamide with glass fibers, and so on. This technology we use for printing some jigs for a serial line, or some for some serial machine, as for example this holder from material ASA, acrylonitrile styrene acrylate. This print time is very short, around 10 hours, and we are able print overnight this part and deliver the next day to the serial production. This was very for us very interested part box for electronic. It was directly printed with the description. Here we use the multicolor system because we need print some 5 different colors. You here see some 4, but this many two description is from a red color, but red transparent material. And the last technology, or it was 2 technology for the printing the polymers, and 1 technology for printing the metals is bound metal deposition. We got this technology on the beginning last year. we are on the beginning with testing this system. System is from the desktop metal supplier named Studio Plus, and the maximum build size is 300 times 200 times 200 millimeters. But the real part size, or the maximum part size, is 150 times 150 millimeters. Yeah, this technology work. We can print some two types stainless steel, one type tool steel, and the new material it's come this year is the copper. Yeah, the technology is very similar as the MIM, metal injection molding, but on the beginning we haven't some injection tools, but we have on the beginning some 3D printer. The main material is in the feedstock, in the rods, as the metal powder is bounded in the polymer in the polymer matrix. And the first we print some part. This gray part, here is the build material, for example, stainless steel, and this material, is the ceramic, and it is as the bridge between the support and the main part. This part must be print with oversized 20%, because in the process shrinkage of this part is around 20%. The first step by post processing is this debinder process. Here is from the structure is eliminated some wax, and the second step in the post processing is the sinter process. For the elimination of this technology, with this technology we can reduction some the weight, because the print characteristic or print philosophy is very similar or is comparable with FDM. It means this technology prints some fixed border, and the inside is filled with this structure, with cubic structure, and with this characteristic we are able to reduce, or this technology reduce some weight. In the sintering furniture, the temperature is gradually increased to up the melting point of the surface of the powder grains, and these grains are connected together. And finished part is here, and the support structure can be with the hand easily to remove without a problem. Here I can show some examples. Here we print some covers for the GPA modules. Here some the compressors for the water injection. This is the part for the new denoxtronic system which we develop currently. And we have here some the small parts from the copper. We tested this material now, and we print some pins, electrical pins, here, or some electrodes for micro-resistance welding. So they are our activities in the 3D print area in Bosch, České Budějovice. Thank you for your attention. And have you some question?
Pavel, you're muted.
I'm sorry.
Yeah.
Always troubles it's lagging a bit. Yeah, so there is one question from Jakub Geyer. Where do you see the biggest benefits in using additive manufacturing in Bosch production?
It's very bright. Okay, the big benefit is the lead time, yeah, for this first part, yeah, with 3D printing, because we can bring the parts early to our customers as the concurrence, yeah, for example, and the parts are from the original material, are can be used directly in the car, but we are not waiting to the serial production, or now serial production, for the prototype steel tool, for example. Yeah, in this area, this injection tools, I see the big benefit.
So are there any products which already uses fully additively manufactured parts currently, or is it just more on the prototyping side?
Only in the prototype areas. Yeah, no directly in automotive industry. Automotive is very conservative, yeah, and we use this 3D printing only in the prototype areas. Yeah.
Can it be foreseen that in several years
Yeah.
some of the parts will be really additively manufactured? I suppose that this is question of costs, no? Maybe for really
and
large production amounts.
cost and the production time. Yeah, because for example, the bound metal deposition is when we print this part, debindered and sintered, we need some 1 week. Yeah, it's very long. For example, the part is printed 40 hours, and the debinder is around 12 hours, and in the sinter often it depends of the volume. It's around 50 hours in the sinter offer. Yeah, sinter machine. Yeah,
of
this
course,
is the
compared to the injection molding
yeah,
or other or the metal manufacturing, which are subtractive, let's say, it's maybe faster.
This is the
But,
big disadvantage. This time, lead time. Yeah.
Yeah, I suppose that with the parallelization of the processes, maybe at some points we will see additively manufactured parts also in the serial production. Okay, are there any more questions from the audience? I don't see any actually. So I would like to thank all the speakers which presented today. But in general, since this is basically the last event of or within the NABIAM projects, I want to thank all the participants in all events which has been organized within NABIAM project, or to all the speakers, to all the participants. And I hope actually that this is not the completely last event which is organized within this consortium. There will be for sure some follow-up project in the future. We during the project we established some cooperations already. There are some ideas for new projects. So I think that the network actually which has been established will be sustainable also in the future. And yeah, anybody can use also those results which will be presented on our web page. And you can also find the videos from the webinars and from the lectures on YouTube. So thank you, and have a nice evening for today. Bye.